I now want to introduce you to another extremely important angular quantity known as angular momentum, and the symbol will be L. It's a vector. Now, just like we had torque is equal to r cross F, we have angular momentum is equal to r cross rho. All right. Now, rho is mv, translational momentum. And so this string of characters you see before you here is very important and very fundamental for rotation. Let's consider implications of this that might be a little surprising. Not how you're used to thinking. So we have a point O, and we're going to have a point mass m, and it's going to be moving along the trajectory of the dotted line here. It's constrained to move along that trajectory at velocity v. Now, perpendicular to that trajectory from point O is radius r. So radius r there is the perpendicular radius to the trajectory in question. That's all that is. But notice that that's the same distance at different locations along here. Well, actually, if you consider just point O, that's what I do want to do. Even when you consider the mass, the point mass being somewhere along here, still, that radius vector has a perpendicular component the same as the one right here. So that's really important in the cross product, r cross mv. So angular momentum, r mv. r being perpendicular to the velocity, and r then is simply the perpendicular distance to the line of velocity. And it's going to maintain that here. It's going to be the same quantity as long as v stays the same in magnitude and doesn't change in direction. In fact, we could be 1,000 miles away, way down here, and still, from the point of view of O, the angular momentum of point mass m about point O is still the same as it was as it passed right across closest to point O. So you normally think that in order to have angular momentum, you would need to have the object moving in some curved or some circular path of some sort, some curved path around O. But it turns out not to be true. It's r cross mv. All right, now I'm showing an extended body here, rotating about point O, and here's a point mass m, radius r, and then v, the velocity, is perpendicular to r. It's a rigid body. And mvr, v and r perpendicular again, is m, v is omega r, times r is mr squared omega. Let's consider that dl, differential angular momentum. The reason I can do that is because even though I didn't explicitly express this as dm, this mass here, this particular ith particle making up this extended body can be considered a differential mass. So then the total angular momentum of the rotating rigid body about point O is the sum of all the mi/ri squared quantities times omega, and of course we know omega is constant for every particle. So as this rotates around, since it's rigid, the particle down here rotates one revolution or rotation at the same rate, so the rate at which the angle changes is a constant, so omega is constant. And of course we know that the sum of those mi/ri squareds is the moment of inertia I. Thus, angular momentum is equal to I omega. And this is the probably as important in angular considerations as the one I introduced to you earlier on, torque is equal to I alpha, where I said that might be the most important one, but I alluded to another one coming up just as important, and this is it. Angular momentum is I omega. Now, we've always been relating this to translational quantities that you know about, so this is very similar to linear momentum is mass times velocity. Angular momentum now is moment of inertia times angular velocity. And now we're going to take a look at how torque and angular momentum relate to each other. So we have torque is I alpha, which is I delta omega delta t. Let's multiply both sides by delta t. So we get torque delta t is I delta omega. Now torque delta t has got a special name, and it is, just like force times time, it's impulse, but it's j theta, j sub theta. We've had j before for linear translational quantities, namely impulse, regular impulse. Now we have angular impulse, and that is change in angular momentum. Just like regular impulse, translational impulse is change in momentum. Now once again, we have that the angular momentum is I omega. So let's take the time derivative of both sides. dl dt is equal to I d omega dt. All right, well, I d omega dt is I alpha. And we know what I alpha is. That's torque. And so we have torque is equal to dl dt. The rate at which angular momentum changes is a fundamental definition of torque. Analogous to the force is the rate at which the linear momentum changes. All right, so now we're ready to define all the angular quantities that I have subjected you to. So we have omega. So we have a spinning disk here, spinning at omega. So the vector quantity, the vector omega, points in this direction using the right-hand rule. So there's omega, vector. Then, of course, well, the new quantity, angular momentum, is also in that same direction. So we have a moment of inertia of this disk, and it's spinning at omega, and there is the angular momentum vector direction. Now, if omega is going up, then we've already learned that angular acceleration is in that same direction, the vector. And now, in order for the angular acceleration to be non-zero, requires that we have a torque, and that really means if omega is going up, then the torque is in a clockwise sense, and so it too has a vector direction in the same direction here. So there's the torque. So that constitutes all the angular quantities that we've discussed and their vector natures.